Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to look at forces on inclined planes. Now in order to look at forces on inclined planes, especially if the object is moving, we also have to look at the process of circular motion. Now here what we've got is an object shown in red, and this object basically is moving in a circular path, basically shown by the yellow circle. Now the thing is, if you take something like NASCAR or an aircraft which is banking, what you're noticing is that it's going to be turning as it goes round a corner. Now for an aeroplane, what will happen is it will bank its wings, and this is where we get the forces of the inclined planes acting. So how is it that it's able to actually make this circular path? Well, basically it's going to be traveling with a linear velocity. Now this can be shown with the blue arrow, v meters per second, and this follows Newton's first law that states that an object will move in a straight line unless a force is opposed upon it. Now basically, if the plane then wants to turn, what will happen is it will bank, and by turning, what will happen is a force will be applied upon it. Now the question is, where is this force coming from, which is going to cause this banking, this turn? Now this force is the same force that basically keeps it going in a circular motion. Now if you took a lump of plasticine on a string and spun it round, there would be a force acting into the center. Now this force is called centripetal force. So the centripetal force holds the mass in its circular path and acts towards the center of the turn. So this is the force holding it, which is allowing it to go in its turning path. Now this is the force which is necessary for satellites to stay in orbit, and in this case the force happens to be gravity. But if you had say an object in a car like in NASCAR going around a bend, there would be a centripetal force acting towards the center. So, and at some funfair rides you get exactly the same thing, where you've got centripetal force acting towards the center. Note, this is not to be confused with centrifugal force, which acts outwards. It's a force acting outward. We're dealing with centripetal force. Now this pull on the straight line velocity basically causes a vector change, and as a result what will happen is it will curve round. So the velocity is going in a straight line, then it's pulled a little bit, which changes the velocity. It goes in a straight line again, pulled again, pulled again, pulled again, pulled again, pulled again, pulled again. The result is we get a circular path. Now because a force is applied on that object, it's also going to be accelerating. So there will also be centripetal acceleration, and this acts in the same direction and uses Newton's second law of F equals ma. Now centripetal acceleration is given the formula v squared over r. So if we substitute that into Newton's second law F equals ma, we then get a centripetal force equation, which is mv squared over r, and we can use this to find out various components of any object which happens to be moving and banking as it moves. So any force acting on the center of the circle can be calculated using that equation F equals ma. For example, look at this jet fighter as it turns a corner. You can see that it's banking, so there's our inclined plane, and it's being pulled round using centripetal force, which is allowing its momentum to actually, its speed to change. Even though it's going in a straight line, it's going to change, causing it to accelerate even though the speed will be constant. So how are these forces drawn? Well, let's take this jet fighter. We know that it's got a mass which will be acting straight down. Now that force acting straight down is the weight force. So there's one force vector that we can put in. We also know that the angle that it's banking at, the steeper it banks, actually more force is going to be generated, which will allow you to turn more sharply, hence you'll be accelerating more. Now in this line what we've got the white line showing the angle towards the horizontal that the plane happens to be banking. So there's our horizontal, and then it's banking in this sort of angle. So that is going to be useful because we're going to be using Pythagoras and trigonometry. Also, we've got a lift force. Now, this is the force acting underneath the wings, which is pushing it upwards. Okay, so we've got weight force acting down, we've got lift force acting up. Now remember, that lift force is going to be greater than the weight force. As a result, it will keep it in the air. That lift force is actually less than weight force, then the whole thing will sink. So we've also got centripetal force, which is acting towards the center of the turn as it moves. So the more it banks, okay, the more the angle changes, the more lift force we've got, etc., etc. So we can work out the various components of force which is applied on an object. So from this diagram, a vector triangle can be produced, where we can see that the weight force is a combination of the lift force, and that will result in the centripetal force acting towards the center. Notice that the angle theta is in between the lift force, or the normal, and the centripetal force. Often the lift force, depending on whether an object is on the ground, is often called the normal. And if you go back to the light unit that we looked at, normal is always at 90 degrees to the boundary plane. So you can see the boundary plane there shown in white, and you can see that the yellow line is basically 90 degrees to this. So once we know these forces, we can then use mass, angle to calculate the velocity using not only trigonometry or Pythagoras, but also the centripetal equation once it's been rearranged. So we can basically work out where our forces are applying on an object, convert them into a vector triangle, solve the vector triangle, and then use these forces to actually calculate a variety of unknowns which we might have. So let's have a look at a quick example. Here we've got an Airbus A380 of mass 500 tons, which is banking at an angle of 20 degrees to the horizontal. And we're going to calculate the velocity of the plane when it's required to make a turn of radius 300 meters. So here's our vector triangle. We've got weight force acting down, we've got the lift force as it banks round, and notice that it's banking at an angle of 20 degrees. So weight force is basically going to be 500,000, but we've got to multiply that by 10 to turn it into a weight force, so we get 5 million newtons acting straight down. We've also got a lift force which is acting at 90 degrees to the resultant, which is at 20 degrees to the horizontal. We've got to calculate our centripetal force, because from that we then can use centripetal force equals mv squared over r and calculate what v is going to be. So from this, centripetal force is going to be the weight force divided by tan 20 degrees. So I can substitute all that in, and I get 13,737,387 newtons. Now you'll notice that that is bigger than the weight force. That makes sense because obviously it's lifting this whole thing up in the air, so it must be greater than the weight force acting straight down. So now I know my centripetal force. We can now use this to calculate V. So I know the centripetal force is mv squared over r. I can rearrange this to get v squared. So v squared will be the centripetal force times the radius divided by the mass, and then I'll just square root it to get the final answer. So I can substitute that in, and when I square root it, I get 91 meters per second, or 327 kilometers per hour. So that just gives you a rough idea as to how we can utilize our force diagrams on an inclined plane and use centripetal force to basically work out an unknown. So here's an example of a NASCAR where basically the cars go around a track, but they're inclined on the bends. So you've got an oval track, and then they're inclined on the apex, and then they're straight down the two sides. So now what we've got is a normal support force which is acting at 90 degrees to the road surface, so that's acting straight up. We've got a frictional force which is actually going to be acting in the opposite direction. That's going to stop it from slipping down the road. We've got a weight force acting straight down. Now friction is very, very important when we're dealing with any form of movement where we've got contact of various objects. You still have friction obviously on a plane where you've got the air passing underneath it, and that's going to generate heat, but it makes more sense when we've got two surfaces which are in contact to each other. Now for this car to be going around a corner, we're also going to have centripetal force which is acting upon it. And as I state here, this will only happen if the car happens to be moving and held in a circle. So friction is basically, it must be overcome in an object in order for a net force to actually be generated. And as I stated, this friction can be in the form of drag or air resistance. So you might have friction acting on a boat, you may have water pushing against it. You've got to move the boat through the water, so as a result, you're going to be generating friction. A plane is going to be moving through the air, so there's going to be air resistance which is generated on that plane. But basically what we've got to work on is the following algorithm, that the net force is going to be made up of the force causing the motion as well as the frictional force which has to be overcome. Now, the force causing the motion will be acting in one direction, the friction will be acting in the opposite. When we take them away, that will give us the overall force. Especially if we want to work out something like force causing motion, we'll get the applied force minus the frictional force. So the idea is that we can use and manipulate this as a vector equation and start being able to calculate a variety of different things. So as I say, if we can rearrange this, we can work out the friction, and then we can then remove that when we put that into our various scenarios. And what I've done is I put in an exemplary video of this, of an example as to how to solve this sort of question. But here's one that we're going to have a look at. In this case, we've got a car of mass 920 kilograms is parked on a hill that makes an angle of 12 degrees with the horizontal. We're going to calculate the brake force that is preventing the car from rolling down the hill. Well, the brake force is literally the frictional force which is going to be acting. So you can see I've got my car in the blue square and it's 12 degrees to the horizontal. So that I've got a weight force acting down, I'm going to have a support force acting straight up, and I'm going to have a brake force acting up the slope. I've also going to have a component of weight force acting down the slope. That's what's pulling the car down. Obviously the frictional force from the brakes is going to keep it sitting up. Those two need to be equal for there to be no net movement. Remember Newton's first law. So from this, I've got the idea that brake force will equal the weight force acting down the slope. So I can find the weight force acting down the slope, and I can draw a vector triangle of this situation. So here's my vector triangle. I've got weight force acting down. I've basically got my weight force acting down the slope, and the angle between that and those two components is going to be 12 degrees. So as you can see from the diagram there. So that basically is my piece of information which I'm going to utilize using trigonometry. So I can find my weight force down the slope because it's the opposite against the hypotenuse. I know the hypotenuse because that's the weight force, so it's 9,200 newtons. Remember, I've got to multiply it by 10, or 9.81 if that's the way you're going to be using to calculate that weight force. So I can rearrange it to find the opposite, or the weight force down the slope is 1,874.5 newtons, which means that the braking force equals the weight force down the slope. So that should also be 1,874.5 newtons up the slope. That means that there is no net movement. So as a result, we can use these inclined planes to produce a force diagram. That force diagram can be converted into a vector triangle, and then using Pythagoras or trigonometry, we can then utilize and find one of those components. The real hard part with this is trying to work out where the angles fit in. And the only way you can get around that is either by using some of your mathematical angle skills or just doing plenty of practice questions. Now, I've also put another video on, linked to this on force, which on inclined planes. So do check those out, and I look forward to you meeting me again. Well, I hope that makes sense. Bye for now.